a few announcements before we begin. Okay, so number one, you remember we have a midterm coming up. So Thursday at 2 o'clock, it'll be posted. Friday at 2 o'clock, it will be due. So don't forget. Second announcement, I put the new homework, number 5, I guess, up on the Google Drive now, and I made it due on March 16. That's a week from tomorrow. So several days after the test. You can wait until after the test if you want to do that one. Number 3, so I emailed the old homework, the homework number 4, back to you guys yesterday. I had one little comment about the old homework that I wanted to mention to you. Okay, so it happens in lots of problems, including one of the homework problems, that we have to calculate some normalization, right? So typically, we have a quantum mechanics problem where I say psi at x and time 0 is a times some function, e to the something, perhaps, okay? And the first part of the problem says to calculate a, right? And so you know that you do a normalization integral. And so you have psi star of x and 0. That's a star times whatever, right? And then you set 1 equals the integral of psi star times psi dx. And this is equal to, we'll say, a conjugate star times a times something, whatever you get from doing the integral. Okay, let's suppose, for example, that this something is 1 over pi. All right, I'll just make up something. Okay, let's suppose that whatever is getting integrated is 1 over pi. Okay, and so this is equal to the magnitude of a squared times 1 over pi. Okay, so you say, therefore, the magnitude of a squared is pi. All right, so now, at this point, we have choices for a, right? We can choose a equals pi, or a equals minus pi, or a equals I pi, or a equals minus I pi, or a equals pi times e to the I phi, right? Where phi is any constant, right? And these things are all complex numbers that have the same magnitude, right? And so these are all numbers that satisfy this normalization condition up there. Okay. Now, normally we choose the positive real one because positive real numbers are kind of easier to work with than complex numbers. So it's a nice, convenient choice. However, I don't want you to think that it has to be a positive real number just because I always choose positive real numbers, right? That's just a choice that I'm making to make our lives a little bit easier. And I noticed it in one of the problems in the last homework. A lot of you had we're starting with something like this, okay, and then said, you then said, what did you say? That psi star is a e to the minus that, right? You didn't have a star on the a, right? You just said it's the same a, right? And then in an normalization integral like this, you wrote with no star, right? You left this thing off, right? And so you just wrote that this is equal to a squared times 1 over pi. And I deducted a little bit of points for that because I wanted to encourage you not to do that. And to encourage you not to do it because someday that will get you into trouble. I'm not exactly sure where it will get you into trouble, but it is bound to get you into trouble somewhere, someday. If you have an a squared instead of a magnitude of a squared, right? Then if you have a complex number for a, like I pi, you're going to think a squared is negative, right? And that's not right, right? So what belongs in an integral like this is the magnitude of a squared, right? And so even though when you're making an arbitrary choice, it's okay to choose the positive real number in a place like this. Still, if you're trying to prove something in general, right? If there's ever an assignment that's a show that kind of assignment, you ought to be considering the possibility that A might be complex, and therefore you need to include the complex conjugate in the psi star, and therefore you need to have a magnitude squared in the normalization integral. Okay, so maybe you guys didn't need this sort of sermon, but I noticed it on several homework problems, and I just wanted to kind of nip it in the bud. All right, so fine. Okay, so let's come back to the calculation that we were working on last week. Okay, so you remember last week, I was trying to show that there are some actual uses for this formalism with the Hilbert space. Okay, and so the first use that we talked about was this generalized statistical interpretation. So the notion that any observable has a set of eigenstates, right? And then an arbitrary wave function can be expressed in terms of those eigenstates. And so you can have eigenstates of energy or position or momentum or other stuff, right? And any arbitrary state can be expressed as a sum of energy eigenstates or position eigenstates or momentum eigenstates, right? Any of those things. And then we talked about what a measurement does and how a measurement will give you one of the results that's on the list of eigenvalues of the thing you're measuring. And after the measurement, the system will be in the eigenstate that corresponds to the eigenvalue that you found in the measurement. Okay, so that's the generalized statistical interpretation. And then we got into a second kind of application of the Hilbert space formalism, which is the generalized uncertainty principle. principle, okay. And so this is a big calculation that I started last week, but I didn't quite finish. I ran out of time before I could finish it, okay. So let's finish that one, all right. And then we'll go on to a third application. Okay, so to refresh your memory, the idea was we have any two observables, like position and momentum. So we'll just call them A and B. And the question is, what can we say about the uncertainties? The uncertainties in those two things. So uncertainty in A and uncertainty in B, right? Is there any relationship between those two uncertainties, the way there is between position and momentum, as we've seen all semester, okay? So in order to answer that question, we got started thinking about what are the two uncertainties, right? So sigma A, the uncertainty in A squared, we know that is the magnitude, no, the average of A squared minus the average of A quantity squared. And this comes out to be equal to an inner product of F with F, where the state F is A minus the average A acting on psi, the wave function that we're in now. So I should say about the uncertainties, sigma A and sigma B in the state psi, like that. Okay. So that is the uncertainty in A, right? And likewise, there's an uncertainty in B. So that's this average of B squared minus average B quantity squared. And that comes out to be the inner product of G with G, where the state G is B, over it, B minus the average of B acting on psi. Okay then, and so then I started trying to make some inequalities for the product of sigma A squared times sigma B squared. So that is equal to the FF inner product times the GG inner product. And based on the Schwartz inequality, this is greater than or equal to the absolute value of the FG inner product, like that. And then I started doing some calculations with that. And this is greater than or equal to this 1 over 2i, the inner product FG minus the inner product GF, like that, all squared. Okay, and now the question was to simplify this thing. And so that inner product, I think this was the last thing I did before I ran out of time. Right? So that inner product, this is A minus average A acting on psi inner product with B minus average B, acting on psi, like that. And then I did a whole mess of simplifications of this thing. And it came in the end down to the average of AB minus the average A times the average B. Okay, so this is, I think, the last thing in your notes from last week, right? Okay, we're actually almost done, thank goodness. Okay, so now the question is just what goes in the other place, right? What goes here as the inner product of G with F? Okay. So that's basically the same argument, right? But now G is the first thing in the inner product. So that's B minus average B acting on psi, inner product with A minus average A acting on psi. And now I can simplify this all just the same way as last week. But basically it means switching all the A's and B's. And so what it comes down to in the end is just to switch all the A's and B's. So it's this average minus the average B times the average A. Okay, so now the difference of those things, right? We want to get the difference of those things to go right in there, okay? So that would be the FG inner product minus the GF inner product, okay? So that is average AB minus average A average B minus the BA inner product minus the average B times the average A. Okay, so now we can finally get to the point. Okay, the point is that the second term in each place, this is just the product of two numbers, right? The average A is a number. The average B is a number, okay? Multiplying numbers commutes, right? There's a commutative law that it doesn't matter which goes first and which goes second, right? Just like you learned in second grade or whatever, okay? So that means that this term cancels this term, okay? Cancels. Okay, but when you have a pair of operators like this, okay, this is not real multiplication, okay? This is the composition of operators, right? That when we write AB like this is a composition of operators. It is B acts on a function, and then the output of that goes into A, right? And so that produces something, and then you take the inner product of that with the original function, right? Over here, you have the composition of operators in the opposite order. It's not necessarily the same thing. Okay, so those two terms don't have to cancel each other. They might or might not, depending on what the operators are. So here we have one average, the A, B average, minus the B, A average. We could write that as the average of the difference, because the average of the difference is the difference of the averages, because averaging is a linear process. Okay, so now this is the average of the difference of these operators written in the two different orders, okay? And I already told you a name for doing that. That is a commutator. So the commutator tells how much the operators A and B fail to commute. So it is the difference AB minus BA. Okay, and so here we see that the quantity inside the average is a commutator. Okay, so the operator inside the average is a commutator. So this is the average of the commutator A comma B. So now we can finish up our inequality. Okay, so we have this expression up here. Oops. This expression up here for the product of the uncertainties. Okay, so what we get is the uncertainty in A squared times the uncertainty in B squared is greater or equal to 1 over 2i. Then there's the average of A, B commutator, this whole thing squared. Okay. So this looks kind of funny with the I there. What I would point out is this average is imaginary. And so this thing divided by I is real. And then when you square it, it is positive or 0. So if this product is positive, it is positive if the commutator AB is not equal to 0. Right? And then there's an uncertainty principle between the two operators. Between A and B. Okay, so if the operators fail to commute, that is, if the commutator is non-zero, then there's some kind of A-B uncertainty principle, okay, that you can't know A precisely and know B precisely. However, it is 0 if the commutator is equal to 0. So then there's no uncertainty principle. Between A and B. So that means we might know both of those things precisely. So we might have sigma A equals 0 and sigma B equals 0. so that you don't have to worry about uncertainty in either of those things. Okay, so depending on this relationship between the operators, on the commutator, whether the commutator is 0 or not, right? That's what's going to tell you whether there's an A-B uncertainty principle or not. Okay, so let's do an example of that. Okay, so our example, the simplest example, is for position and momentum. Okay, so if X, no, if A is X and B is P. Okay, so that's it's negative IH bar d by dx. Okay, so if we want to know what the commutator is, we let them act on a test function, right? I already showed you this calculation. I'll remind you how this goes, right? That you know that X acting on P, acting on f of X, that means X acting on negative I H bar times the derivative of P, called f prime of X, like that. Okay, so that is negative I H bar X f prime of X. By comparison, P acting on X acting on f of X, okay, that is negative IH bar d by dx of the quantity X f of X. And so we have the derivative of a product. So we remember to use the product rule for that. Okay, so that is negative IH bar. And let's see, it's the first times the derivative of the second plus the derivative of the first times the second. So that is negative IH bar X f prime of X minus IH bar f of X. Okay. So that tells us then that the commutator XP acting on f of X is equal to XP f of X minus PX f of X. So that is this thing minus this thing. So the f prime terms cancel, but what doesn't cancel is this remaining term from the product rule, the IH bar f of X. Okay, so since we know what the commutator does to f of X, right, for arbitrary f of X, right, we know what the commutator does to any old function, right? What the commutator does to any old function is multiply the function by IH bar. Okay, so from that, we can deduce that the commutator is the operator that just means multiply by IH bar. Right? Multiply any arbitrary function by IH bar. Okay, so that's that's the position momentum commutator, which we knew about already. Okay, and so then from that, we get that the uncertainty in x squared times the uncertainty in p squared is greater than or equal to 1 over 2i times the xp commutator, so I h bar all squared, and that is h bar over 2 squared, right? Because the i's cancel. So if I take the square root of both sides, that is sigma x times sigma p is greater than or equal to h bar over 2. Okay, so this is the Heisenberg uncertainty principle for position and momentum. Right? And this is something that we've been talking about all semester, and you have checked in lots of examples. Right? And we've seen some examples where it's right at the limit with the equal sign, and we've seen other examples where it's beyond the limit, right? That the product of the uncertainties is greater than h bar over 2. So this is a proof of something that I've been telling you all semester. But more than that, it tells you that this is one of a big family of uncertainty principles, right? This is not the only uncertainty principle, but there's a family of uncertainty principles whenever you have a non-zero commutator. That is, A and B do not commute. The commutator is not equal to 0. There is a word for that people sometimes use. People call these incompatible operators, meaning that they don't commute, right? Or I guess these would be called compatible operators, that they do commute. So anytime you have a pair of incompatible operators, you will have an uncertainty principle between those operators. So that's a nice payoff from doing all this formalism, getting to know an uncertainty principle that we didn't know about before. Okay, let's see. So let me get to the next example. Do I have another? Yes, I have another example. What if you have, that's for another example, if you have the Hamiltonian for a free particle. Okay, so that is H is P squared over 2m plus nothing. Okay. So independent of position. In this situation, we have that H, the commutator of H and P equals 0. Okay. How can we tell that, right? Let me show you how to tell that by means of doing some manipulation with operators. Right? Here, HP, is this thing? Okay. HP, this is, this is P squared over 2M commutator with P. Okay, so this is P squared over 2M acting on P minus P acting on P squared over 2M. This is P cubed over 2M minus P cubed over 2M. This is 0. Okay, so from this, you could see that for a free particle, there is no uncertainty principle between H and P. Okay, but what about between H and position? So if we want H and position, okay, that would be P squared over 2M commutator with position. Okay, so that's P squared over 2M X minus X P squared over 2M, like that. Okay, how do we do that? Okay, so this we could write as, well, I'll just factor out the 2M. That doesn't really affect this commutator. So that's just a number, mass, that factors out. Okay, so here, the first piece, this is a P acting on P, acting on X. Okay. For the last piece, I'll say this is minus X, P, P. Now, if I want to use the information that we already have about commutators, a clever trick would be to add and subtract something. So I'll say minus P X P plus P X P. That's clever because I just added and subtracted the same thing. And so for sure it's correct, okay, it's equal. And then I can simplify what's written here. This is now 1 over 2M. And in the first red and blue things, that is P acting on P X minus X P. And then in the second pair of red and blue things, okay, this is P X minus X P acting on P. Okay, but now I know. What is px minus xp? This is the px commutator. And the px commutator, well, the xp commutator is IH bar. So the px commutator is negative IH bar. So this is negative IH bar. Likewise, this is negative IH bar. So putting these things together, this is 1 over 2m, and we have p times negative IH bar minus whoops, where did I go wrong? Oh, I see where I went wrong. This is a plus, not a minus. Oops. Sorry about that, guys. That's a plus, not a minus. Okay, so it's all of this plus negative IH bar P. So this is, let's see, there's two copies of the same thing. I'll cancel the 1/2 in the front. Okay, so it's 1 over m times negative IH bar P. Right. Okay. So it's not equal to 0. Okay. So that goes to show that there is an uncertainty principle between H and X. This is for the free particle. Okay, so I'll say for the free particle. Okay, so that's a little further payoff of the general formalism, right? Is that it shows us that in this example of a free particle, there's a energy position uncertainty principle, but there's no energy momentum uncertainty principle. To tell you a little bit more about that example, right? That is to say the state e to the ikx for the free particle. For the free particle, the state e to the ikx, or a times e to the ikx, is an eigenstate of energy, right? We worked that out when we were solving the free particle. Okay? And it is an eigenstate of momentum. Okay, so that means it has a specific energy, which is h bar squared, k squared over 2m, and a specific momentum, h bar k. Okay. So since it has a specific energy, it has sigma energy equals 0. Or I'll call that sigma h. Sigma h equals 0. And it has sigma p equals 0, right? It's a specific energy, specific momentum. Okay? So certainly sigma h times sigma p equals 0. No uncertainty principle. But a to the e to the ikx is not an eigenstate of position. So the sigma x is not equal to 0. Okay, so there is an uncertainty principle between position and momentum, or an uncertainty principle between position and energy, right? This thing that has a perfectly defined energy and momentum has a terribly defined position. It's spread out everywhere on the x-axis. So sigma x actually goes to infinity. Okay, so that's the generalized uncertainty principle. Okay, and now let me show you a third application of this Hilbert space formalism. Okay, so, and this will turn out to also involve commutators, although that's not obvious at the beginning. Okay, so for a third position, let's talk in general about how an expectation value, any expectation value, changes with time. Okay, so let's think again about any arbitrary observable. Q. Okay, and so that means it has an average, which is this average of Q, right? So that is the inner product of our state psi with Q acting on psi. Okay, so now suppose we want to know about how does this thing change in time? Okay. So, mathematically we would say, what's the derivative of that with respect to time? Okay, so the time derivative of this average Q. Okay, so that means the time derivative of psi acting on Q psi. All right, so this is the sum of three terms, okay? And let me try to explain that. Let me write out what this is, and then I'll try to explain why the thing that I'm writing is true. Okay, so this is, and the textbook will tell you that this is the sum of three things, which is d psi dt inner product with q psi plus psi inner product with dq dt acting on psi plus psi inner product with q acting on d psi dt. Okay, so the textbook says that as if it's obvious. Maybe it's not obvious to you. Let me try to justify that statement, okay? Why is this statement true? Okay, well, let's go back to what the inner product means as an integral. Okay. Why? Okay, so if we have the time derivative of psi with q psi, okay, so that means the time derivative of the integral over x of psi star of xt with the operator q acting on psi of xt integral dx. Okay, so it's the derivative of an integral, okay? Now, because the limits of integration are not changing with time, we can take the derivative inside the integral, okay? And so this is the integral of the time derivative of a product, psi star times q acting on psi, integrated dx. Okay, now this is the derivative of a product, okay? So for sure, you can use the product rule. Okay? So based on the product rule, this is the derivative of the first. So d psi star dt times q psi plus psi star times the time derivative of q acting on psi. Okay, so now you're thinking maybe you've never seen an operation like this before, where it's the time derivative of an operator acting on a function, okay? And so now you're wondering, well, can you take the time derivative and just put it inside and say that, you know, the time derivative of q acting on psi is equal to q acting on the time derivative of psi? Well, that's usually true. That's pretty nearly always true. Okay, so in the normal situations where that is true for linear operators, we would have, it is d psi star dt times q acting on psi. Okay, now I'm going to leave some space and I'll say plus psi star times q acting on d psi dt. Okay, so if q is something like a position, right, then we would say, well, you're multiplying by x that can go before or after the time derivative. No problem. Or if q is a momentum, then you're taking a derivative with respect to x. And the derivative with respect to x can go before or after the derivative with respect to time. No problem. Okay. The only situation where there is a problem would be for a really weird operator. Okay, and it would be for a really weird operator that actually has time built into it. right? So if the operator were something like multiply by the time, okay, then you couldn't pull it out of the derivative like that, because then that would violate the product rule, right? You'd have to use the product rule for a time derivative. Okay, so to include the weird situations where you have an operator that explicitly depends on time, I can write this extra weird term in the middle. I will say it is psi star times dq dt times psi of xt, like that. Okay, and so this is for a weird operator that explicitly depends on time. Okay, so this is not a normal thing, right? This is not a thing that we have done at all this semester so far. As far as I can think of, this is not a thing that we will deal with at all in the future this semester either. So this is a weird thing, and I wouldn't even mention it except that the textbook has it. And if I leave it out, you'll wonder, why do I disagree with the textbook? Okay, so I'll keep it in. Okay, and then if I keep it in, then I have the sum of 3 terms, and each of them looks like an inner product. Okay. So the first term is an inner product of d psi dt with q psi. The second one, the weird one, is the inner product of psi with dq dt acting on psi. And the last one is the inner product of psi with q acting on d psi dt, like that. Okay, so this is maybe not so obvious after all, but that's, that's what I was writing up over there. Okay, so that this is the sum of 3 terms, of which the middle one is a weird thing that you may never actually see in real life. But the first and the third are certainly real things that you'll see in real life in this semester. Okay, so now, we have these time derivatives of psi. But we know about time derivatives of psi because that's what the Schrodinger equation is all about, right? Time derivatives of psi. Okay, so the Schrodinger equation tells us that IH bar times the time derivative of psi is equal to the Hamiltonian acting on psi. Or in other words, if I just divide through by IH bar, that d psi dt is 1 over IH bar times the Hamiltonian acting on psi. So I can put that into the first and third terms there. Okay, so therefore, the time derivative of this expectation value of Q, what is it? Okay, well, we have the expectation value, the inner product of 1 over H bar H psi, right? That is this thing, right? Inner product with Q psi. Plus the weird term, which is psi inner product with dq dt acting on psi, plus the final term, which is the inner product of psi with Q acting on the time derivative down here. And that time derivative is 1 over IH bar Hamiltonian acting on psi. Okay, now what? Now we can simplify this a little bit by factoring out the constants, right? We have constants there and there, okay? And we can pull those things out in front of the inner products, okay? And you know, when there's a constant in the front half of the inner product, in the front half there, that changes to an integral where you take the complex conjugate of everything there, okay? So when you factor out the constant, you pull out the complex conjugate of that constant, right? And so the complex conjugate of I is a negative I. So this is negative 1 over IH bar H psi inner product with Q psi plus the weird term. Plus 1 over IH bar psi inner product with Q acting on H, acting on psi. Now we can simplify this a little bit more because the Hamiltonian is a Hermitian operator, okay? And so we can use the properties of a Hermitian operator, that it can fly from one side of the inner product to the front of the other side of the inner product, okay? So this is now negative 1 over IH bar psi inner product with H acting on Q acting on psi plus, let me put this non-weird term up next. Okay, so 1 over IH bar psi QH on psi, and then plus the weird thing. Psi dq dt psi, like that. And now what? Now we can see that our first two terms have the Hamiltonian and Q acting on psi in different sequences. So they look like the commutator of the Hamiltonian and Q, whatever the observable Q must be. Okay, so we have then that this time derivative that we're looking for, that's equal to negative 1 over I h bar. And then we have the commutator of h and q inside the average, and then plus the weird one, right? So psi d q dt, psi. So these things are both just averages, right? And so we could write this as, well, here, I over h bar. So negative 1 over I is just I, okay? So the average of the HQ commutator plus the average of dq dt. Okay, so you remember that this thing is 0 for most operators. Okay, so for those not so weird cases, we see that the time dependence of the average Q depends on the commutator of H with Q. So this is another way in which commutators, are really important for quantum mechanics. Okay, that the time dependence of any operator depends on whether or how that operator commutes with the Hamiltonian, right? The Hamiltonian is special among all the operators in the world, right? Among all the operators in the world, the Hamiltonian is the one that goes into Schrödinger's equation, right? Unlike all these other operators, right? And so the Hamiltonian is special. And so the way that an expectation value evolves in time depends on how the corresponding operator commutes or doesn't commute with the Hamiltonian. And in particular, if Q commutes with the Hamiltonian, that is to say, if HQ equals 0, then the time derivative of the expectation value of Q equals 0. And the way we say that in physics is that this expectation value of Q is conserved. So in your previous courses, you've learned lots of examples of things that are conserved, right? So in university physics, you talked about conservation of energy, conservation of momentum, conservation of angular momentum, things like that, right? And so here you can see that the analogous things in quantum mechanics are depending on commutators, right? That it depends on whether something that you're interested in commutes with the Hamiltonian or not. Okay? So to see some examples of that, one example is for the conservation of energy. Okay, so the energy, that is the expectation value of the Hamiltonian. So the time derivative of that depends on the commutator of the Hamiltonian with the Hamiltonian, right? So that is HH minus HH, right? Well, that is 0, right? Any operator commutes with itself. Commutes with itself. And so, therefore, energy is conserved. So the time derivative of the average H equals 0. Okay, another example. What about conservation of momentum for a free particle? Okay, and so if you want to know the time derivative of the average momentum, that's equal to I over h bar, the average of HP commutator. But I already showed you that the HP commutator is equal to 0 for a free particle. That was back earlier in this class, right? A few minutes ago, I showed you this, right? And so, therefore, the time derivative of the average momentum is equal to 0. So, momentum of the free particle is conserved. Okay, and so, you know that in classical mechanics, right? So that a particle starts moving with some momentum and it keeps moving with that momentum. That's constant. Okay, but then for one more brief example for this class, what about the momentum of a particle in a simple harmonic oscillator? Okay. So in that case, this dp dt, the derivative of the average momentum, is this I over h bar, average of h with p commutator, where this h is p squared over 2m plus 1/2 m omega squared x squared. Okay. And now the commutator of h with p is not equal to 0. All right, it's not equal to 0 because h depends on x right up there, right? This term messes up the commutator. And I think we talked about that back when we were talking about the simple harmonic oscillator earlier. Okay, so the HP commutator for a simple harmonic oscillator is not 0. So that means this time derivative of the momentum in a simple harmonic oscillator is not equal to 0. So the momentum of the particle is not conserved. And you already know that from classical mechanics, right? Because in a simple harmonic oscillator, a particle goes back and forth, right? And so its momentum is sometimes positive, sometimes negative, right? As it's going back and forth, right? The momentum of the universe is conserved because when the particle gets a little bit of momentum going one way, the Earth has momentum going the other way, right? So the momentum of the universe is conserved, but the momentum of the particle is not conserved. And so here you can see that enters into quantum mechanics in this commutator approach. Okay, I will stop talking now. And I've run out of time. So I will see you guys tomorrow. And we can talk about this kind of stuff a little bit more. And I'm going to show you a new kind of notation tomorrow also. In addition, if you have any questions about review for the midterm, feel free to bring those tomorrow. I will invite questions from any of you. And so, we can even do that at the beginning of class. And so if you have review questions, please ask them. If you don't have any review questions, I will just teach you new stuff. Okay, so let's plan on that for tomorrow. All right, see you then.